So today we're going to be trying out support vector machines. So first, this is just a video to explain what they are and a little bit more detail into the algorithm. The objective of a support vector machine is to find a hyperplane in n-dimensional space that separates and classifies a set of points. So the way you can think of a support vector machine is a road machine, where we have a road and we've got the cars on one side and the cars on the other side, the pavement on one side, the pavement on the other side, the buildings on one side, the building on the other side, and we want to separate those by the widest road possible. And the objects very close to the road or to the center of the road, so the cars and maybe a couple of the closest buildings, they're what we call the support vectors. They have quite a large influence on where the division of the road sits. So to spread the two classes of data points, there are many different planes that we could pick. If we think about this in the case of 2 dimensions, they would be straight lines. So the objective is to find the plane that maximizes the margin. So that means there's the maximum distance possible between the two sets of data points. The reason for this is that maximizing the margin distance means that we have some reinforcement so that future data points are more likely to be classified correctly. So the hyperplanes are decision boundaries that help us classify points. Data points falling on either side of the boundary are attributed to different classes. The dimension of the hyperplane depends on the number of features or variables that we put in. If the number of input features is just 2, then our hyperplane is a straight line. And that's the examples that we're going to be looking at. If the input number of features is 3, then we end up with a plane. And if we increase the number of input features further, then it's kind of hard to imagine what the plane would look like. So the support vectors are the data points that are closest to this plane. They have the biggest influence on the orientation and the position of it. We use the support vectors to maximize the margin of the classifier. Deleting any of the support vectors would have a big impact on the position of the classifier, and it's these support vectors that we use to help build our support vector machine. Let's look at the case for 2-dimensional space. You know that a straight line can be written as y equals mx plus c, but if we translate this into x1 and x2, we can write it as this. The dots above this line will satisfy this formula. The dots below the line will satisfy this formula. Assuming the label y is either +1 for green or -1 for red, all the 3 lines below are separating hyperplanes. They all share the same property that above the line are the green points and below the line are the red points. And they satisfy the separate hyperplane constraint, and that's what's written mathematically here. This is the perfect scenario, the linear separable scenario. And this constraint can be met by the support vector machine in this case. So what's the margin? The margin is the smallest distance from any point on either side of the hyperplane to the hyperplane. The optimal hyperplane will give the biggest margin. After we've constrained and ensured that each of the classes of data points are on either side of the hyperplane, we need to pick the optimal line to maximize the separation. We do this by optimization using quadratic programming, which I'm not going to go into here, but if you give it a quick Google, there's quite a good Wikipedia page on this. So to sum up, the support vector machine in linear separable cases, we need to constrain and ensure that each observation is on the correct side of the hyperplane. Then we need to pick the optimal line to ensure that the distance between the points and the dataset is as large as possible. We can also use support vector machines in the non-linear case where we have points that can be separated by a hyperplane that is non-linear. And to do this, we use the kernel trick. There's some really complicated math here, which I'm not going to go into. But again, if you give it a Google, there's some pretty good articles on it, and feel free to ask me any questions. So you're going to have a go yourself now. So I put the tutorial up, so give it a go and let me know what you find.